Now we're going to start chapter 25, section 4, energy stored in an electric field. First of all, for a capacitor, we will apply potential energy equation and also we'll apply energy density equation. So this is the another density, but it is energy density, and the reason we do that is because we're saying energy is stored in the electric field, and you're going to see the relation between the electric field and the energy density once we get that equation. So first of all, we will use what we learned before. Energy is, specifically potential energy, is charge times potential, and that comes from the definition of potential, which is energy per charge, right? And so this is the general equation. Now we're going to think about parallel plate capacitor, for example. And let's move some charge from one plate to the another, okay? And since the total charge of the capacitor is Q, we are not moving all the charge. We are going to move some charge, and let's say it's infinitesimally small charge, and that charge is dq prime. This prime is not a derivative. It's just to show that it is a charge Q, but it is not Q because you already have the Q as the total charge. Okay, so that's why we're using prime. So using the above equation again, since we have a very small charge, that's going to give us very small potential energy. And we also know that from the electrical equation, Q is equal to CV, right? And then you can write V prime as Q over C, but this Q is Q prime. So that's what we have in the parentheses, Q prime over C. And that's like the charge you are moving divided by the capacitance. And the total energy stored in a charge capacitor can be found when you integrate this for every charge on the plates, right? Because you are moving all of them. So that's why the interval of the integral is going from 0 to Q, the total charge. And you simply have Q prime dq prime integral here, and C is constant, it comes out. And then the Q prime becomes 1/2 Q square. And that's why energy is equal to 1/2 Q square over C. It can also be written 1/2 CV square using again that equation Q is equal to CV here. If we do that, we have CV square divided by 2C. One of those C's are going to go away, and you have C left at the top, and V square comes in, and there's 2 at the bottom, as you can see this equation. So basically, when you have the capacitor, the energy can be either found from Q 1/2 Q over C, Q square over C, or 1/2 CV square. Either way is fine. So if I'm given the charge, I can use the first term. If I'm given the potential, then I can use the second term. The other could be constant, but they will give you the they will equal to the same thing. And we have a couple questions to answer, and then we will think about this in terms of energy density, so that you'll see it's related to the electric field. So you can think of this energy as being stored in the field, and the reason, again, we'll see it. If we consider two parallel plates, energy density is like any density, right? We know from mass density as the mass over per volume, and we learned about charge density depending on the charge distribution. If it is 3D, then it is charge per volume. If it was 2D, it's per area. 1D was per line, per length. And here we have energy density, and it is per volume because if you think about the parallel plates, the space between them is where the volume is. So if you kind of calculate this space here, okay, it's like three-dimensional space, you can find out the volume. That's where the energy is stored. And again, let's say like this is negative Q plate and this is positive Q plate. Those are the plates, the capacitor that forms the capacitor. Okay, So since the energy density is energy per volume, we are going to show the energy density as a small case u, okay, and it is equal to the energy over, again, the volume. Okay, it's nothing that, like, you don't really need to memorize it. It's like the density, it's the quantity is energy, so you're going to have energy at the top, and then depending on the dimension, since it's spread out the volume, we divide by the volume, so it's a three-dimensional case. So from this, and for the capacitor here, this is the spacing between them, right, D, and one of those plates area is A. Then you can find the volume by just multiplying D and A. So that volume is simply, I kind of want to write volume because V, I don't want you to think that this is the potential or voltage. So volume is A times D, and that volume is this volume where the spacing between the plates are. So then if we write this energy density equation, it's the energy itself divided by A times D, right? That's what we're replacing with the volume, and that will be equal to, before that we learned about U being 1/2 CV square, so we're going to put that in, CV square at the top, 2 is at the bottom, but we also have AD at the bottom, so this is what we have so far. And now we are going to replace C and V. Let's just write what C and V are. C is for the parallel plate capacitor, ignoring the electric constant, or basically saying kappa is 1. We have epsilon naught A over D, and the potential difference, since they're parallel plate, E is uniform, and again, this is simply the magnitude. We don't really care about that negative sign in capacitors, because we are not trying to look for the electric field direction or anything, but if we need it, we can also use it. And this is, again, this V is equal to ED is only true for constant uniform E fields, okay? So if you put these together and then replace that energy equation, we are going to get, so let's just write it, C is epsilon naught A over D, and V is, so this is C, V is E times D, and we also have at the bottom 2AD. So I'm putting everything in parentheses so we don't confuse what is at the bottom, what is at the top. Looking at this, the area are going to go away and these are going to go away, and then what do we have left with? 1/2 sorry, I forgot to square V, and I was like, why do I have this? Let's see. So this is squared, so this D is gonna go away as well because there are two of those. And I should not have left with D, so that's why I remember the square here. So this was V and it was squared. So what we have left with is 1/2 epsilon naught and the electric field square. So that's what the energy density is. So you can see that it depends on the electric field. Okay, so that's why we say energy is stored in the electric field, and this is the energy per volume, and it only depends on the electric field. Okay.